Hello, everyone. My name is Arman Tadevosyan, and I would like to give a talk on the Gaussian assignment process. My talk is based on our joint work with Mikhail Lifshitz, and which is currently published only as preprint. So the structure of my talk will be the following. Firstly, I will introduce you to the statement of what is random assignment process. Then we will consider Gaussian case and define Gaussian assignment process itself. And later on, we will look at the properties of this object. And finally, we'll take a look at some pretty pictures obtained by numerical simulations. Please feel free to interrupt me if any question arises. Just ask and I will try to answer it. So let us start. Firstly, I will introduce you to the statement of random assignment problem. Suppose that we have n workers or n employees and n jobs that should be completed by employees. And for simplicity, suppose that for each employee I and each job j, we know how much time required for employee I to commit job j. Let us denote it as xij. And actually, we have complete bipartite graph. Then h has weight xij if and only if employee I spent xij time to complete job j. So our natural task is to assign each job to each employee in such a manner that there is no possibility to share same job between two different employees. So we assign each job to each employee and order them to start simultaneously doing the jobs. And we can ask various questions about this structure. For example, we can sum up all the times xij, and it would be some complete time of performing all the jobs. So, for example, we could want to minimize overall time. In case then all xij are the income of the company, then employee I perform job j, then we want to maximize their sum of incomes. There are many examples of how we can treat dates xij, but the main observation is the following. If xij are basically the numbers, then it's not hard to apply some linear programming algorithm, for example, Hungarian algorithm, to obtain optimal solution. But in the real world, people usually have some uncertainty in their views. For example, one can say that for completing the job J, he have to work 30 minutes plus or minus 10 minutes. And that's the uncertainty. We know that he would work 30 minutes on average, but we want to take into account that plus or minus 10 minutes. So, for example, we can put on each edge of this graph a probability distribution. And, for example, we can see that the first employee can do first job quite fast if we treat, for example, the whole edge as the interval of 1 hour. And for example, this man can perform this job approximately in 30 minutes. So seems naturally, I think. Okay, let us specify our problem. Consider a square matrix X. Those entries are independent and identical distributed random variables, xij, that are sampled from some distribution pi. and associate with each permutation pi of the set 1, 2, etc. n the following sum. S of pi equals to the sum for I from I1 to n xy pi I. So it is required to study the properties of the random variable maximum S of pi and to find optimal permutation pi star such that the actual expectation of the maximum S of pi is obtained when we compute expectation only on the S of pi star. So in this case, we call permutation pi optimal. In our work, we specify problem more and say that if our distribution pi actually equals standard normal distribution, we call such process a Gaussian assignment process. And we want to understand which properties it has. So the picture is the following. It's quite messy, but I think everyone can understand what it is. So, okay. But firstly, before talking about properties of the Gaussian assignment process, I will introduce you to the history of the problem. In 1987, Metzard and Parisi proved for the case that the distribution pi equals to uniform distribution on the unit interval that the expectation of the minimum S of pi converges to zeta of 2. Then the zeta is zeta function, zeta Riemann function. In 2001, David Aldous proved that when we have standard exponential distribution, then the expectation of the minimum S of pi also converges to zeta of 2. But in a Gaussian case, we haven't convergence to some constant. Instead, we have that our expectation of the maximum S of pi is equivalent to the n square root of 2 times log n. So we also could say that the expectation of the minimum S of pi equals to the minus that variable. But since our distribution is symmetric, we can only consider the case of maximum. Okay, now I will introduce the main result of our work. And it formulates in the following way. Let S be Gaussian assignment process defined in a way of the previous slides. Then it's true that the expectation of the maximum actually equivalent to the n times square root of 2 over log n. And we obtained this result in the 2 steps. The first step was upper bound, and the second step is lower bound. So upper bound was not quite hard because it required to just apply Jensen inequality and some estimates on the Laplace transform of our variables. But in order to prove the lower bound, we met some troubles, but eventually we resolved them by introducing greedy policy. And now we'll talk about greedy policy. Consider the following greedy policy of constructing a random permutation pi star. Let us denote I in square brackets, just the set of 1, 2, and etc. I. Then we will define our permutation inductively. First of all, we define pi star on the first element as the argument of the maximum x1j. And then by induction for all I from 2 to n, we define pi star as the argument of the maximum xij, but only over those j which wasn't in the previous values of pi star. I will provide you with an example of how it works. Consider 6 by 6 square matrix, and we want to apply greedy policy to that matrix. Here I represent cost matrix X. So at the first step, we take the maximum value in the first row. I denote here maximum value as the green square, and the entries that I won't take just as yellow squares. So on the next step, we prohibit all the squares in that column to choose further. And on the next step, we take the maximum value in the second row, but if we had maximum value in the second column, we just simply ignore that because it is in a column which is unavailable to choose. And so on, we ban the fourth column and repeat this process many and many times till we get the first step when we have no choice but to take that element. So we have some pretty nice properties of this greedy policy. It can be shown that expectation of the maximum has lower bound of expectation of S of pi star, which is n times square root of 2 log n plus big O of n. So therefore, we obtain the main result, and in particular, we get that expectation is obtained on this permutation. Also notice that S of pi star is actually the sum of independent random variables. So we can normalize it by subtracting its mean and dividing by its standard deviation. And thus we can apply central limit theory to get the properties of its convergence. If we subtract an from S of pi star and divide by bn, then it converges in distribution to the standard normal distribution, where we can write down the asymptotics of its mean and variance. And also we can write down some good rate of convergence of this random variable such that the supremum norm of the difference between our cumulative distribution function and cumulative distribution function of the standard normal low actually grows no more than big O of 1 over square root of n. We prove, we apply central limit theorem to the specific variable S of pi star. Okay, let us proceed. And some auxiliary result of our work is the modulus of continuity. We investigated its properties. First of all, let us tell some definitions. The Hamming distance between two permutation is dh between pi and sigma, which is equal to the sum of indicators where pi of I is not equal to sigma of I. So if two permutations differ in almost all positions, then this distance is quite large. And in opposite, then two permutations coincide in almost all positions, then the distance is approximately 0. and denote the pair Sn and Dh, the set of all permutations endowed with the metric Dh. So it becomes metric space. And we can consider balls in that metric space. We denote them by BH centered in pi with radius r. And after that, we get that for a modulus of continuity, which is such expression, expectation of the maximum of absolute difference between S of pi and S of sigma. The sigma lies within the ball centered in pi. For this modulus of continuity, we get that we actually have two-sided inequality. There, the functional part actually coincides, but these constants are different. And in our further work, we will find the optimal constants in these inequalities. So I will formulate theorem once again for any pi permutation and radius from 3 to n. They are asymptotic estimates then n approaches to infinity. Expectation of the modulus of continuity is actually not less than square root of 2 over 8 r square root of log n. And this thing is not greater than 4r times square root of log n. As I remember, here not. Okay, and the final thing I want to talk are the simulations, numeric simulations. But firstly, I will introduce some technical details. Suppose we have distribution calligraphic M on square matrices n times n such that X sampled from distribution M if and only if all the entries of this matrix are independent, identical distributed normal variables. And let us denote by Hn of X the result of Hungarian algorithm run on a cost matrix X, and by Gn of X the result of greedy algorithm, which we introduced previously. When we can get estimates of the expectation by averaging this, the values computed on the samples, and we can plot them, we get several lines. I will zoom it up for the simplicity. Here we see the following lines. The green one is the main term in asymptotics. We obtained n times square root of 2 log n. This one is actually the exact upper bound of the expectation. And this one is the lower bound obtained by greedy algorithm. And we can see that here is a blue line. It's the result of Hungarian algorithm. And also I draw some approximation to the result by simply shifting the main term the main term of asymptotic and precisely specifying its second term of asymptotics. So we can see that actually on a linear scale they are quite near, and on the logarithmic scale we can see that our upper and lower bound are actually good, in order to approximate the ground truth, which we think is Hungarian algorithm here. Thank you for your attention. Well, I had to mention that this T, the number of samples, was something like 300. So for each size of the task N, we solve T problems and then average them. So for each N here, we had solved 300 problems and then average them. Currently, we are working on the case that we have variables like sigma times standard normal, so we can model the uncertainty. But it's actually quite a hard problem to solve. They are not identical distributed, but we will try to do it. But always you can, for example, at the beginning, like shift and scale your variables in order to get the normal standard. If, of course, they are normal.